All right, great. We reached the number, so let's start. It's my pleasure to introduce our speaker today, Dr. Christian Wolff from the EPFL in Switzerland. Christian is a scientist at the Photovoltaics and Thin Film Electronics Laboratory and a leading researcher developing perovskite PVs. He has a PhD from the University of Potsdam and got a Marie Curie Fellowship at the EPFL. Today, Christian will share insight on linking structural properties to photovoltaic performance in halide perovskite multijunction solar cells. Christian, thanks a lot for joining us. The floor is yours.
Yeah, thanks a lot also for the invitation and opportunity to present our work on this nice webinar.
Our pleasure.
Also, welcome everybody to the talk. Thanks for making it and for showing interest. If it doesn't interest you, no hard feelings, just close and see you next time around on a different topic. As mentioned, I want to talk about how structure of materials, in particular perovskite in this case, impacts the way the performance of a perovskite-based multi-junction solar cell rolls out. And so in essence, what we want to do here is in the beginning, simply take a look at two things that are maybe obviously, but maybe not so obviously interrelated, namely really at the nanoscale here on the left side, you can see a high resolution electron microscopy image of a perovskite polycrystalline film with different features that you can see. So you may have these gray blobs here, then larger structures that we then identify typically as grains. You can have these stripes here. And what I want to take a look at with you today is how this then correlates with what we then measure on a device, so typically a GV curve. And we start off with a very, very simple system, almost one of the archetypical ones. So maybe the older among us, they started out with methyl ammonium lead triiodide, but there was soon a movement towards different compositions, and one of the simplest ones that were discovered something like 10 years ago were based on cesium and form a medium lead triiodide. And what we did in the experiment, maybe something like 2 years ago, is simply look at what happens to this nanostructure if you simply exchange the form medium in the polycrystalline film with a little bit of cesium. So in this case, this is the control with 0% cesium, 15, and then 30. Yeah? And you can already tell just, even if you're not an experienced electron microscopist, you can see that there's something different. So here there's a lot of these stripes, here less so, here almost none, and also these speckled areas are getting less and less. And so what you can do with high resolution electron microscopy, in addition to taking a look at the direct pictures, sort of take the Fourier transform thereof. Of course, we don't just do the Fourier transform of the image, but instead we do a diffraction. So a selective area diffraction pattern. This then looks as such. So you can see that we are creating these speckles where we have a lot of contrast. So this means there's a lot of diffraction, which then tells us, okay, we have high crystallographic order. This is the case for all three of the samples, but then the devil is in the detail. And you can identify quite a few additional features, such as, okay, here we have this smearing out of these lines. And what the smearing out means is that the distance between the diffractant planes is very close to the ones, or it's very close to where they are supposed to be, let's say, but not quite. And so you have a little distribution around, let's say, the optimum if you would have a perfect crystal. In addition to that, you can sometimes see that you have almost a perfect squarey shape, but every now and then there is something that is like off shape. So you can have additional phases. And in this particular case, we realized that you can index these phases relatively easily through their reciprocal distance. And there we realized that this is a delta phase, a specific one, namely the one of cesium lead triiodide. What we also realized is that set up and tuning the cesium content, that for some of the mixtures, there was almost a perfect diffraction pattern for many of the grains. So this is a singular one, but we looked at hundreds and hundreds of them. And here you can see you have a really nice, almost cubic pattern with almost no smearing and very few additional phases. Yeah, so you could say this is sort of the sweet spot when it comes to the cleanliness of the crystal. So we identified sort of these three regions where we either have stacking faults in the case of low cesium content that gets less and less, up to the point where we have essentially no stacking faults at the cesium concentration of roughly 15%. But when further increasing the cesium content, we realized that we form additional phases, and we identified those then as delta phase of the cesium lead triiodide that does not intercalate into the Fa crystal. So it's just too much there, and they have a mixing limit. Now, you may ask, okay, this is all nice, but what does this have to do with the device? And this is what we set out to understand. And so Mustafa created these PIN structured single junction solar cells in the first place, where we have, I guess many of you are familiar, glass covered with ITO. We deposit thereupon a self-assembled monolayer that acts as a whole transporting material, in this case MEO2 packs. Then the perovskite is solution processed, as it was also before, and then we complete the stack with the electron transporting or electron selective layers, namely C60 and tin oxide, and silver as the back electrode. And what you can do with such devices is take a look at their spectral response. And if you are equipped well, such as was the case with our collaborator in Swansea, Stefan Zeiske, you can really measure also very, very low signals. So this is the normalized external quantum efficiency that you can see here on the left side for varying, well, devices with varying cesium content. And we were able to get with this very nice setup measurements down to 10 to the minus 7. So this means we have like 1/1,000th, a tenth of 1/1,000,000th of the signal that we have in the spectral range. And so this allows us to also get signal well below the band gap. And what you can see here is that you have these sort of two bumps in the low energy range. And these are signatures of two things, namely that there is absorption, well, three things if you wish, namely that A, there is absorption below the band gap, so there must be some sort of states, and B, they create charge carriers that then can also be extracted because EQE measurements are current measurements. That means the current needs to leave the device in order to be detected. The reason for these two bumps is a different one, so it's not like we have localized energetic states that create just one particular defect state at 0.8 electron volts and one at 1.2 electron volts relative to the valence band in that case. But this is an optical effect. So you have a cavity, right? So the light enters from the bottom, is then partially, or to the greatest extent, reflected at the backside, and then you are creating standing waves in the stack because it's a very, very thin absorber compared to the wavelength. And then you can have these cavity modes. So it's a little bit like the resonance that you use in a Bragg reflector, or like the resonance in a Bragg reflector is maybe the easiest. And so already by just looking at them, right, so this is a log scale, you can see that there are differences, maybe on the order of one or two, one order of magnitude. And you can also analyze this a little more in depth. And this is exactly what we did. So we integrated these bumpy areas. And what we saw is that you have a negative correlation, so anti-correlation between the cesium content and what we call a sort of trap density. We normalized that to the case with cesium 0. And so now if you have states in the band, within the band gap, and they are optically active, they will most likely contribute to recombination. And so we were relatively happy to see that we have a somewhat reasonable correlation also with the device performance then, where we saw that, okay, if you have a high amount of these in-band gap states, you have low open circuit voltage on average, whereas if you then decrease the amount of these trap states, you have a increase in the open circuit voltage. I wrote here this partially explains the effect. I think there is more to it. We carried out a more in-depth optoelectronic analysis to find out whether this is sufficient. You can already mathematically say that it's not, right? So if you have a change of any recombination induced effect by an order of magnitude, so 10 times more, you should not expect a VOC change of something like 200 or 300 millielectron volts, but maybe more like 60 to 100, depending on your ideality factor. But we saw more than that. And the reason being that in addition to recombination, we then also have, in addition to bulk recombination, we then also had more surface recombination in these devices. Okay, so open circuit voltage is not everything. So our solar cells are not supposed to create only voltage, they're supposed to create power. And so you can ask yourself, okay, what happens then to the power? And what we saw is that indeed a low open circuit voltage then also translates into a low performance. But even if you have a somewhat high open circuit voltage, and this is by no means a record or anything the likes, you can still have a performance loss. And then upon further analysis, we saw that this intercalation of these cesium delta phases also created barriers for charge extraction. So in addition to voltage losses, we then also had additional transport losses that were happening. And so it's really important to hit the sweet spot in terms of composition to maximize performance. And I think a lot of groups have done this empirically without really looking at the nanostructure, but I think it's important to make this link. And then, as many of you know, a question that is still looming with regards to can perovskites be commercialized or not is their stability. And so it was also a natural question for us to check how these stacking faults and or delta phase inclusions impact the stability, and we did this in two ways. So on the one side, we simply took a larger set of cells, so these are our averages here, and placed them under one of our solar simulators at something like 35 degrees in open circuit. So this is a test that I recommend to you if you don't have the capabilities of doing maximum power point tracking, because it's a relatively straightforward thing to do, right? So you take your cell, place it under a solar simulator with or without temperature control, and take it out and measure it in several time intervals. This is nice in two ways. So as said, for one, it's a relatively simple setup to do. You just need a lamp, if you are being honest, in addition to what you already have. And second, one thing that people often don't realize, so now we are thinking a little bit ahead, if you have a module and it's being installed in the field or on the roof, prototypically, your installation is not going to be connected to the net straight away. And what this means is that you have exactly the scenario that I'm just talking about, right? So you are placing the cells and modules in the light under open circuit, and then they are just sitting there for a little while. Yeah, so exactly the scenario that I'm explaining here on the left side. Right. What we saw is that also with regards to stability, we had a clear dependence on the composition where fortunately, not fortunately, it's direct correlation to that. The devices with the absorbers with the least defects were also the ones that were the most stable. This is not just under open circuit, but then also if you track their power. So we then took another set of devices, and I see that the main author of the study is just joining online, so very nice. Hi, Mustafa. Yes, so also when you do MPP tracking of these devices, in this case, we went a little bit harsher. So yet again, one sun roughly, LED-based light. But then we elevated the temperature to something like 85 degrees and did the whole thing not in nitrogen this time, but in air. And we could also see that the degradation for the devices, so here it's a little bit of a simplified graph because otherwise it would be extremely busy. The devices with the cleanest absorber of sorts, so the one with 15% cesium in them, appear to be the most stable. What I want to stress is that this is not unique to the system that we have been looking at so far, so the cesium-Fa binary system, but Mustafa also looked at other systems that are floating around in our lab that we use for different purposes. Most famously, we have here this triple cation mixed iodide bromide system, both as a standalone that was, I want to say invented, but coined by Michael a couple of years back. And then more recently, this even more complicated triple cation, triple halide system with a bit of chloride inclusion has become famous. And irrespective of which composition we have looked at, for almost all of them, we do see these striped contrasts that we then identify readily as stacking faults. All right. So the reason why I'm mentioning this is that so this is not an exclusive thing for our study, but it is also important for other absorbers, in particular the ones that are maybe a bit more tandem relevant than the sort of too low band gap cesium Fa system that I mentioned just now. Okay, so now we looked at really the grains, and how the local structure impacts the performance and stability of devices. I want to go one step further, and to do so, I want to swiftly introduce to you two measurement techniques that we used. One is a relatively simple one. So this is a photograph from back when I was a PhD student, where we had here on top a glass fiber. Out of the glass fiber or into the glass fiber, we coupled a blue laser shining onto a perovskite sample. And here in front, you can see this yellowish looking glass. So this is a long pass filter. And what this does is it blocks the laser light, but it lets through the emission that comes from the perovskite. So what we are looking at here is photoluminescence. On the other hand, there's another technique that we often use, which is force microscopy based. In this case, I want to point you towards this graph here. So we are having this little cantilever that scans across the surface. Doesn't have to be in a scanning mode, can also be on a larger scale, but in order to resolve some of the nanostructures, you need to have high spatial resolution. And what we do with this is we scan the topography, and then in a second scan we lift the tip. And if the tip is conductive and we can connect it to the bottom of the substrate, what we can do is we can measure sort of the potential difference between the two. And in this case, we call this Kelvin probe force microscopy. And this gives us then a map of the surface potential. How this typically then looks is as such. So the optical measurements are a little bit lower in resolution just because of diffraction limitations. So you can see here a PL image where we just integrated the intensity for something like a 120 micrometer by 120 micrometer image. And on the lower side, it's more on the micrometer by micrometer. So here you can already make out sort of the domains that we already looked at in these polycrystalline films. And what we realized is that there's quite a bit of inhomogeneity, but there is a chance of homogenizing that with different tricks. So I'm hopeful that many of you are familiar with the recent literature. So there's all sorts of chemical passivation strategies, washing away unbound surfactants, passivating defects such as interstitials or missing halides at the surface or anything the likes. And so what we chose, and I will not go into too great detail about the chemistry because I don't think this is important here, but what I want to say is that we are able to, despite having this inhomogeneity from the start, homogenize the surface in a second step. And what we did here is we, in particular, looked at the ways to homogenize the surface in a first step, but then also thinking of a device in the next step, also the interface between this surface and the next layer. And this is what we want to take a look at now. You can do this on a nanoscale. This is what I've shown you here. So we have a homogenization from left to the right. If you then go one step out, so you zoom out. So now we're at the centimeter scale. Here we just have two devices. So this is a prototypical substrate of ours. And here's another one. So we just had two side by side, and we do this photoluminescence imaging once more. This time we took effectively the logarithm thereof. So like this, you can then calculate the non-radiative loss. Now we first look at the perovskite as it is. Then we have a signal and a bulk plus a little bit surface loss, somewhere in the range of 130 milli-electron volts, it should say here. What happens in a device is that next we would put then an electron transport layer on top. I forgot to mention that this is already on the whole transport layer, so losses from the whole transport layer are already included if there are any. But what is more drastic is that once we put the adjacent electron transport layer, so C60, is that we see a drastic reduction in the photoluminescence. Yeah? So in this scale, it doesn't seem like a lot. Yeah? So we go from somewhere around here, minus 130 milli-electron volts, to somewhere around here, minus 200, 220 milli-electron volts loss. And it doesn't seem crazy, but if you would take a look at the photoluminescence by itself, so this is a log scale thereof, you would have a loss of 2 orders of magnitude. Yeah? So that means instead of 100%, 1%. That's basically dead in terms of photoluminescence. Good thing is we have, as I just mentioned, found a way to A, homogenize the surface, but B, then also passivate exactly this loss from happening. With a trick that we call surface and interface passivation. Here we did an in-between step where we took a look at, okay, do the individual parts suffice to do the job? So is it sufficient to just have surface passivation or just interface passivation? And the answer is yes, to some extent, but the best job is done when you are connecting the two. Yeah. What I think is also very important, and it's not super obvious here, is that we have here created on the N-transport side, and this I think is very new, a scenario where we have completely eliminated losses. On the contrary, we are not 100% sure yet whether this is just an optical effect, but what you can see here is in the case of SIP, we have even increased the photoluminescence, right, in particular. So this means that it's not a loss anymore, but we are creating a scenario where we have more emission coming from the absorber plus transport layer stack, which potentially allows for higher open circuit voltage. We then took this to the device and took a look at the open circuit voltage, and indeed what we have just seen in the photoluminescence is then also translated. So that means we are not having any issues to extract the charge carriers that are now not being lost due to recombination. And so we were able to boost the open circuit voltage in the full device by something like 100 millivolt. In the case of surface and interface passivation, and then if you combine the two, you get an additional 20 millivolts or so. What happens often is that you are sacrificing this improved interface by giving rise to some fill factor or transport losses, but in this case, this was not the case. The reason being the exact molecular structure. If you're interested in it, we can talk about it in the Q&A session. But with this surface and interface passivation, we were able to effectively harness the fact that the molecules that we bind onto the surface are sitting such that they are creating a direct pipe high stacking with the C60, and so there is virtually no transport loss, as you can see here from the in fact enhanced fill factor. The reason for the enhancement of the fill factor is yet again a reduction in recombination, where we then benefit from the pseudo fill factor boost to the fill factor directly. This doesn't just work in a single junction. So we took this newly developed absorber plus surface and interface passivation and put it into a tandem with crystalline silicon and a heterojunction, a crystalline silicon cell that we fabricated. And what you can see here is that, okay, we can directly harvest this benefit. This then also translates into very efficient devices we call it small scale. I know some in the community that do single junction would consider this already a larger scale device, but for us, this is rather a small scale device where we could improve up on our record something like 1.5, 2 years ago, around 31%. Now we are more in the 32% range. And I think this is really nice. So the devices I've shown you before, these are single junctions. They are also a little bit smaller, but yet again, we are able to transfer this homogeneous passivation from the millimeter to the centimeter scale. And now the question is, can you take it even beyond that? And the answer is yes. So here we then took it to, I wouldn't call it extremes, but extremes with the equipment we currently have at hand. So what you can see here on the left-hand side is a photoluminescence image of a tandem that is on a full wafer. So this is something like 10 centimeters across. And what we can see are a couple of things. So we have these blue stripes, right? So these are the bus bars. Then you have the thin blue stripes. These are the finger lines to collect the charge carriers that are photogenerated. And then there is a few futile spots where we still have imperfect passivation and or some sort of damage that happened to the perovskite. But overall, it's a very homogeneous emission, which you can also see if you take a look at the histogram, right? So you have these small bumps stemming from the bus bar, and then here probably the fingers. And then the greatest majority still gives you a very narrow distribution of emission. This then translates also into the optoelectronic device performance. So here we have now something like 60 square centimeter device. So it's a 4-inch wafer where we could mostly preserve the high open circuit voltage, very high fill factors, and the majority of the loss is essentially just coming from the current. The reason being exactly these bus bars that we have to live with because of the large area we need to transport the current away. And so there's just a shading that we can't get rid of. We didn't just measure these high performances in-house, we also sent a couple of these devices out for certification. So one of the good ones in the low area range gave us a certification around 32%, 31.7 if I remember correctly. And then we're very proud that we got a 28.9 also on such a beautiful device on a full wafer. Now, all of this is nice, and I really think that the community has done a fantastic job in combining different techniques to create all sorts of beautiful structures where we typically, at least for the tandem case, discriminate between these 3 scenarios. So we have the front side flat devices, so the silicon is textured in the back, but on the front side it's flat in order to be as close to the flat substrates that we typically use in single junctions. Then on the opposite side thereof, here on the right, there is the fully textured scenario, which PV Lab also pioneered now already 7 years ago, where you can nicely see that the perovskite, which in this case is deposited via a hybrid route, which means we vapor deposit in the inorganic template and then convert it into a perovskite via the use of the organic organohalides from solution. And in between, a little bit more recently, up on modifying the structure, the size of the pyramids, a lot of people have now started working on these so-called buried structures. Buried meaning that the pyramids are buried, right? So you're not putting the solar cells in the ground or anything like that. What Dennis realized in a recent study that was just been accepted, so you'll be able to read up on that in a couple of days, I hope, is that there is at least one in between there, and we call that curved or undulated structure, where you can see, right, it's not fully flat. Okay, there's a little bit of curvature maybe here already, but it's also not the fully textured scenario. And we thought that this was a really interesting case study to take a look at what happens to different thicknesses with regards to performance, in particular optically. So let's take a look at the optical champions, so to speak. So we have here the hybrid fully textured case, and we will compare it now to the curved devices that we have fabricated. Let me mention that this is still completely solution processed, and the texture sizes were not adapted whatsoever. So these are our standard texture sizes from PV Lab. Some silicon companies may have slightly larger ones, but there is no such thing as an industry standard. So it's somewhere on the order of 2 to 3 micrometers in height, these pyramids. Yeah, so these are standard silicon pyramids. What you can take a look at now is just the geometry of the surfaces. And this is exactly what we did. So we took a look at from the valley of the perovskite to the tip, how the surface angle changes, right? So if you would have a, let's say, perfect pyramid, such as is the case in the in silicon, it would be sort of like a distribution, it looks like this. So you have a very, very narrow at one angle, a distribution close to 1. But this is not the reality with the perovskite, not even in the hybrid case. Yeah? So in the hybrid case, you tend to have higher angles. Yeah? So you're closely following the silicon, which comes in at around 54 degrees. Yeah? So we're just scraping above 50. So there's a little bit of flattening, but only just. But then there is also a few other angles in between. But overall, we have higher angles, and the distribution is thereby also a bit narrower. If we compare this now to the case with the curved perovskite, there we have lower angles, and the distribution is overall a little bit wider if you were to normalize it. Why is that important? That is important because you will be facing the scenario in a potential tandem module that the solar cell by itself, so this is not even a solar cell, right? So this is just a perovskite on silicon, but the solar cell by itself does not directly face the sun, but there's something in between. Namely, there's typically encapsulation and glass in front of it. And what this creates is the opportunity to have a total internal reflection upon a, let's say, initial reflection of these optically imperfect surfaces, and then the chance of a second absorption. And in such a scenario, maybe a lower angle because of the higher refractive index in here is not a bad idea after all. This is what we wanted to test, also based on simulation results from our colleagues in Karlsruhe at Uli Petzol's team. And so the way to go is to test this directly with a encapsulated cell. So here we have the test structure. You can see it here on the bottom. So we wanted to be optimistic. So we didn't have any textured glass around. So we even added an anti-reflection coating. Then we had glass, encapsulant, TCO, the electron transport layer stack, the perovskite, and the silicon beneath. And then the only thing we did is we just measured the reflection of such a stack. Yeah? So if you have improved internal reflection and then a chance to reabsorb, then you should see this by the light not being able to be emitted from the overall stack, but being absorbed at least somewhere in the stack without thinking about where for the moment. And so this is a very simple experiment, right? You just go to the UVS spectrometer and measure the reflectance. That's it. And we did this for the four devices or 4 structures that I mentioned earlier. Yeah, so we have here the fully flat in black, where you can nicely see, okay, the perovskite sort of acts like a good anti-reflection layer for silicon. So we are able to maintain a somewhat low reflection in the range where the perovskite absorbs effectively. But as soon as you are entering the range below the band gap of the perovskite, so where the silicon should absorb, all of a sudden significant reflection sets in, and you even have these interference bumps. If you go for the other structures, so the buried one, where the perovskite fully covers the silicon, you can improve upon this scenario. But even better, if you want to stick with full solution processing, is to really go for these curved structures that we have newly developed. They are not quite as good as the fully textured scenario with the hybrid approach, but I would say they are very close. And if you would calculate how much current you're losing here, it's on the order of 0.5 milliamps per square centimeter overall. So the takeaway message here is fully flat in a module configuration with front side encapsulation is drastically reducing the performance of a tandem device, whereas the other configurations are doing much better, with the buried being outperformed by the curved and only slightly losing to the hybrid absorber deposited with a more complicated approach. Now the question is, can we also make efficient devices with that? And the answer is yes. So the devices that I've shown you before were still based on a fully flat silicon or frontside flat silicon. And now we have created these devices with the texture and the undulated curved perovskite structure on top, and we can effectively maintain the high performance that I've shown you before. So with this, I'm practically already at the end of my presentation, but I want to send you then off after the Q&A with a little bit of a question in particular, because I know that a lot of the audience here that listens to Fluxim is also interested in simulating such devices. And I want to ask whether, if you take a look at the structure that you see here on the left, right? So we can start with the flat one. Here it's somewhat maybe still justified. So you see here the perovskite on top of a silicon wafer. But especially in the case of the bottom part, you really need to ask yourself, is an effective medium representation of such a structure really going to give you meaningful insights into a device that you then simulate as such? And I would argue that we will have to think in the near future, especially as probably even other, possibly even more exotic structures will be emerging, whether this is a reasonable thing or whether we need to open the toolbox again and think of simulating at least in 2 dimensions, right? So this is sort of a 1-dimensional plus maybe optical 2-dimensional stack that you are simulating, not just ZFOS, but also many other tools. Is this enough, or do we need to have variable thicknesses, possibly even taking a look at what spatial heterogeneity, such as grains and grain boundaries, are doing to our drift diffusion simulations? With this, I want to conclude. So in the beginning, I've shown you that local heterogeneity down or from the unit cell, so starting essentially from the unit cell, or how the unit cells stack on top of each other, impacts the performance and also the stability of at least the lead-based perovskites that we have looked at, but that there's hope that you can modify and improve thereupon either by compositional tuning and this is maybe a little teaser for the next time around, or for example, some of the conferences that are coming up, you can also modify that upon modulating the crystallization, for example, with additives, where Mostafa has a paper in the pipeline right now. The second part, I spoke about how these heterogeneities expand beyond just the local structure, but that they also impact the optoelectronics on the nano, micro, and then millimeter scale. We looked at photoluminescence and then the surface potential or work function of perovskite surfaces and how they can be homogenized via these surface and interface passivation agents. This enabled us to make very nice devices, both on a millimeter, centimeter, but then also wafer scale. I think this is a really nice demonstration that surface homogenization can take you a long way. And then the last part, I find these new structures that we have seen, so these curved undulated structures, very interesting. They are, I think, important because at the very least, they point towards scenarios that may happen in a production unintendedly. So if you are texturing a big wafer with, I don't know, 300 centimeters square, so 250 centimeters square, with wet chemical etching, you have a certain degree of control about the height of the pyramids, but it's very likely that somewhere on this large area, there's still a large pyramid forming. And then you may have the scenario such as the one that we actively sought after here, namely these curved and undulating structures. And I think it's really important that we also understand these somewhat outliers that probably will still happen in a fabrication scenario. And in that context, also think about whether or not it makes sense to describe these polycrystalline, partially different thickness films with an effective medium approach when we are trying to model them. With this, I want to thank my team. So this is a photograph from already a little bit over a year ago, Christmas party at the end of 23. So we are having a lot of fun from time to time. Today, I've shown you work from these 3 gentlemen. So Mostafa is our expert in electron microscopy. Kerem takes pride in looking at different surface interface passivation agents to boost performance. And Dennis has discovered these beautiful undulating structures. They're part of the overall team. With this, I want to thank the funding agencies that provide us with the means to do this research, but then also all the collaborators from around the world, spanning from Australia to Saudi Arabia, but then also very local ones, such as the ones here in Switzerland, in particular at Fluxim and at ZHAW. And last but not least, of course, you for spending this morning with me.
Thanks a lot, Christian. This was an amazing presentation. Thanks also for mentioning SetFos as a tool to simulate, at least partially simulate your structure. Meanwhile, I've seen there are still 120 researchers interested in your presentation in the Q&A. So let's jump to the Q&A. I've seen there are plenty of questions. Let's start from the beginning. Okay, this one is a question for one of your first slides. Why are C60 and SNO2 deposit over perovskite? Is asking if it's possible to deposit only C60s.
Can you repeat it, or maybe I can?
I think it's on slide 5 or 6. You have a structure with this one. Both they are asking if it's possible to use only C60.
Okay, so this is a device fabrication specialist question. So luckily, I used to make a few devices myself. So the answer is yes, but it comes at a price. So if you do not deposit anything between C60 and silver, such as tin oxide, so this is one layer that we chose because it is then also compatible in the next step with tandems. So it helps us with stabilizing the C60 or protecting it from whatever comes next. So we would typically then sputter with a plasma or RF sputtering system that is relatively aggressive, a TCO on top, so it protects from sputter damage. You could also put BCP in between, which will help in stabilizing the interface between silver and C60. You can make devices even without that. They will work, they will be rectifying, but you will have slightly lower performance. So I would advise against that.
Yeah.
The reason being, so BCP helps with modifying the work function of the electrode.
And there's a question for the next slide. You have been showing a normalized EQE. They would like to know if you have also the IQE for the subband gap absorption.
IQE. The answer is no. The reason being that at least with the tools that we have available, we cannot measure absorption with such high precision.
And also, if the PCE losses are dominated by the fill factor or the ISC.
So I didn't bring these. I didn't bring these statistics today. You can read up in the paper. It's published already. So the short circuit current was the least impacted by the variation. Of course, upon adding cesium, you are slightly increasing the band gap. But overall, I think the relative change there was relative, yeah. So relative change there was something like 5%, so less than 1 milliamp per square centimeter, which is way outperformed is the wrong way. So the losses are dominated by the recombination and the transport losses in this case.
Yeah, sure, makes sense. I've seen here there's a question from Imalka. Christian, how do the losses change with addition of MA? Is there a reason not to add MA? And he say that he can think of thermal stability, but there are also studies on both temperature cycling and thermal stability studies with the MA composition.
Yeah, great question. So this was sort of the reason why we also looked at the compositions containing MA. So the reason why Mustafa, the PhD student, chose not to is twofold. I think it's if you are trying to look at something very fundamental, it's good to have a simple system. That's argument one. And then we have an internal debate which goes exactly along the same lines. So I think that having small amounts of methyl ammonium helps in homogenizing the system. but Mostafa is not convinced by that yet, and so he believes that removing MA altogether will ultimately prove to show the best performance and stability. And yeah, this is how it goes between supervisor and PhD students. They need to argue against you and hopefully prove you wrong, because then we have learned something new. With regards to thermal cycling, typically, right, you cycle up to 85 degrees. I think up to 85 degrees, you will not see drastic changes for a reasonable number of cycles. Above that, probably you do. Yeah.
Great. And now there is a question from Fan Fu. Hello, Fan Fu. Thanks for joining us as well. He's asking if CES 0.25 is an outlier in terms of VOC and stability.
Yes, 0.25. 0.25 or 1.5?
Right, in 0.25, maybe Fan Fu can confirm.
Is this from literature or from our results? I don't see this.
Yeah. Let's keep it for later. Let's move forward to another question from Imalka. I think this one is a little bit further down. It's asking if the passivation being used on the texture cells, or do you see a similar improvement? Oh, yeah, if you use passivation in the texture cells.
So, I mean, I mentioned I didn't want to go into too great detail. So, but I can mention, so the surface passivation, there's nothing super special about it. This is the perfluorinated, well, it doesn't have to be the perfluorinated, but that proved to be then yet the most effective. So this is the perfluorinated phosphonic acid that we also used in our previous studies. And so the answer is yes. As for the interface passivation agent, this is a piperazinium-based salt, which is then also very likely depositable on textures. So to answer your question, we haven't tried it for the IP and the SIP combo, but I'm relatively optimistic from experience with the SP.
Mm-hmm. Okay, now I see a question. Well, probably you can reply quickly. How can we control the lattice mismatch between layers in tandem solar cells?
Yeah, fantastic question. So far, at least from our side, I can say we did not. And that is a problem, right? So in particular, in view of what Imalka just asked, so thermal cycles that are naturally occurring outdoors, if you were to put the cells on the roof, or even if you go even crazier, let's say in space. So what will happen is the different thermal expansion coefficients will create effectively strain in the systems. And if you match them and they have a certain modulus, so the capability to expand and contract, then they can compensate for the strain. But we haven't done that so far. I happened to have seen just last week a beautiful publication from Meng Li and Antonio Abarte's team, where they did exactly that. So there's a nice demonstration where they looked at the bottom interface of the structure, right? So they tailored the MEO2PAX alternative, so it's another self-assembled monolayer, in such a way that it lattice matches the perovskite. And so I believe that this is a nice approach to improve the growth of the perovskite. And then in a second set of experiments, I think it'll be interesting to see how tough or not so tough bonds at the bottom and then top interface impact the lamination, delamination behavior up in thermal cycling. Because for me, this is not so obvious to see whether you want to have extremely tough interfaces necessarily, or you want to have some sort of maybe a molecular spring there that compensates for some of the strain that naturally occurs. But it's an important question.
Yeah. And here another one. Why do you see high PL intensity at lower edges of the module?
What's this? I guess you're referring to here, huh?
I think, yeah, probably yes.
I would have to go back and take a look at the setup. It could be that it's not perfectly flat, so it's a little bit tilted, and then the lower part is a little bit closer to the camera, so getting either receiving a little bit more light or just having favorable emission into the camera system. But otherwise, I agree, it's a little bit surprising, right? So at near the edges, where you may or may not touch your wafer, you typically get lower signal and not higher signal.
Yeah, there's now when you're collecting TEM images of the crystalline film, some regions show crystalline, another region not. What could be the reason for that?
So I think I understood the question right. So why do some parts appear crystalline and some parts do not appear crystalline? So the answer is that you are looking effectively only along one crystal plane. And so this is the geometry of the electron microscope in transmission. If you were to tilt your sample a little bit, you would be then able to take a look along a different, what is called zone axis, and then you would see more crystallographic contrast from other domains. So effectively, the crystal of the grains is not oriented such that you have high contrast with the direction of the electrons chosen in this geometry, but tilting the sample will give you also higher contrast in the other planes.
Yeah. And also asking you, what's the fabrication route for the perovskite? So if you are using spin coating or blade coating?
Yes and yes. So we have now, I think, closed the gap. So at least in my team, we do not do hybrid inkjet yet. You never know. But other than that, we are fabricating devices in the team with different routes. So these samples were fabricated with spin coating. But then other colleagues in the team are working on the mentioned hybrid route where you do evaporation and then solution processing. Another colleague is working on vapor depositing perovskite, so sequential vapor or PVD, CVD techniques. So we do all of them, and then more recently we have also looked into blade and slot die coating, or will look soon into slot die coating. Have a new system in the lab, but it's not yet fully operational.
We are running a little bit out of time. Another couple of questions. They're asking you if machine learning can accelerate the discovery of optimal passivation material for interfaces.
I mean, we have not worked in this direction too much yet. I don't think I have that slides here straight away. The answer is yes. We'll stop. Our experience in this regard is, however, limited at the moment. So what I can say is that this nice lady here on the front row, Hilal, she has been working in this regard. So she created 2 sets of robots that enable us now to very, very rapidly screen through different compositions, but then also different passivation or additives in the fabrication process. And so the preliminary results tell us that, okay, we can screen something like 50 different compositions very efficiently. And with that feed, for example, a machine learning algorithm, what we have not done yet, but others have, so I would refer you to Tonio Bonassisi and Xijing Sun's work, is to have maybe a density functional theory backbone that sort of predicts, okay, this may be a good candidate for surface passivation. Please try it in an experiment, feed that back, and like this then create maybe an optimization loop. We haven't done that yet, but the guys at MIT have. So I think it's a good route and should be explored more.
Makes sense. All right. We still have a lot of questions, but now it's late. I would like to close this session, and thanks a lot again, Christian, for joining Fluxim. Our next webinar will be on March 18th at 10 a.m. We are going to change topic. We are going to discuss about all the display design with Dr. Peter Livermore. So I'm very looking forward for this event as well. Thanks again, Christian, and thanks for everyone for joining. I will see you soon.
Thanks a lot. And reach out if you have more questions.